Hey everybody, welcome to an introduction to OpenGL workshop. I'm Alex, I'm the project officer. And before we go into some of the more meaty details, I want to give a couple of ACM announcements. A quick, I guess, social plug before we get started. We have, multiple social media profiles where we, typically post events and what's going on in the realm of ACM UTSA. Our Discord is the most updated avenue, so I would suggest you join it. We typically are more up to date with our events announcements in there. You can find that at discord.acmutsa.org. But we also keep our other socials active. Just not on Discord, you're more likely to get, more frequent updates. And moving on, brief membership plug here. Membership is free so long as you attend 9 meetings in the fall, or 9 in the spring, right? Yeah, 9 in the spring or fall. And there's a couple of benefits you get from being a member. You get a shirt at the end of the year. You're invited to our end of year banquet. You're eligible for giveaways and so on and so forth. If you have not become a member, I'll give you a second to either go to that link or scan the QR code. Oh, and also a brief update for those of you who are members, T-shirts and stoles. So those of you who are graduating will be distributed at the banquet. So yeah. Okay, moving on. So a couple of upcoming events. We have one on Wednesday, one from MITRE. They're coming over and they're going to talk about how to diversify your skills for career readiness. Look forward to that. Maybe you can connect with whoever's speaking at that event. I think it'll be good. It'll be in HSU 2.212. That is Harris at 12 p.m. This Wednesday. And of course, we have our weekly ICPC meetings. So that's for competitive programming. Those are held Sunday, 11 a.m., usually for about 3 or 4 hours, but you don't have to be there the entire time. And it's online, or you can go into NPB 4067, and we'll also be there. Continuing on, we also have a Women in STEM panel featuring more people from MITRE. That'll be next Tuesday on the 26th at 4 p.m. Still figuring out the location. We also have another event with the steganography guest speaker, and he'll be speaking to us about what he does and stuff about steganography. I think it's really interesting. That'll be next Tuesday, an hour after our MITRE event on that day at 5 p.m. And then we'll have our final workshop of the semester, an introduction to embedded systems. So we'll cover Arduinos, we'll cover some basic electrical components. So you kind of, so we build an interest. And maybe if you're curious, come on and join along. And also we have our ACM Social. We're still figuring that out. That's April 27th at 4 p.m. So that's the same day. So it's next Wednesday at 4 p.m. I hope I'll see you guys there. There's also the spring banquet. So here's the kind of the big announcement. It's Sunday, May 1st at 1 p.m. We would prefer you come in, or we want you to come in business casual attire. And the only real qualification is that you have to be an ACM member. Make sure you save the date. And finally, end today's meeting. If you have not already, I'll leave that link and that QR code for a couple seconds so you can get that in. Everyone all good? Okay, I'll post it again at the end, so don't be too worried if you missed it. Going forward, let's start with our introduction. So first things first, I think context is important. So the question is, what is computer graphics? Well, computer graphics is essentially the study or the way in which we render images or visual data onto the screen. An example here is this really lovely visual made by Delay Felino. This is the kind of stuff you can do in computer graphics, right? But it's also beyond just making pretty images, right? There's video games. There's, there's GUIs, right? So how you interact with the computer daily, right? So computer graphics is, I don't think you can overstate how important it is simply because it's something that's everywhere. We don't think too much about it. And this process of, getting an image onto your screen, this is typically done through a graphics processing unit or GPU. Sometimes you have an APU, and that's onto your CPU. So if you have a laptop that typically has like graded graphics, that is your graphics processing unit is within your CPU. But the question now is, how do you actually draw all this stuff, right? How do you, get all this information onto the screen? How do you interface with your graphics card, right? Well, this is typically done through graphics APIs, right? And what they are is they're essentially a way to interact with the hardware that renders all of your images. And typically, there's a couple of standard APIs. There's, you may have heard of Vulkan or OpenGL or Metal. Those are graphics APIs or libraries used in computers very often to get those images onto your screen. Usually, for example, like video game consoles, they might have their own graphics API, because it works best for their platform. Like, for example, the PlayStation 3, I believe that had its own graphics API. But for now, our focus is OpenGL. The question is, why OpenGL? Well, even though it is a little outdated, like a lot of people in a lot of games do prefer using Vulkan, OpenGL is still perfectly acceptable. And it's still decently modern. And I think there's just a lot more tutorials out there, and it's easier to get started in OpenGL. But the problem with just using graphics API like OpenGL is that there's a lot of setup to do. So, sure, you have all these functions that kind of detail you, drawing graphics and drawing triangles, but you need also a lot of setup, right? So you typically use other extension libraries to help you draw windows or call in other OpenGL utility functions. And this is what we're going to do today. We're going to use GLFW and GLAD as our main APIs to interface with OpenGL itself. And I guess before I continue on, I've actually posted a GitHub repo with directions on setting up OpenGL. If you'll post that link, Nico. But I can show it on stream anyway. I've made a GitHub repo here, and I'll update this later with our examples that we'll walk through. But here I kind of tell you the prerequisites and what you need to set up OpenGL and all of our libraries in Visual Studio. And so just to make things easy, these are directions, and the three main APIs or prerequisites that we want is GLFW, GLAD, and GLM. I didn't mention this, but GLM is typically used for mathematics. It's an easier way to kind of do all the mathematics required for computer graphics, since there's already functions there, there's already structures there, and they already have vectors and matrices, which we'll talk about a little later in this presentation. But this is here for setup. But before we dive into actually talking about OpenGL, I think the first thing we should do is actually make a window. So let's get started with that, shall we? So I have a couple of examples here, and like I said, I'll push these later to the GitHub. But your setup for Visual Studio, I don't know if you can see that terribly well. Yeah, I'll zoom in. But our setup looks something like this. When you make a new project, this is probably going to be empty. The first thing you have to do is just make a file by right-clicking and adding a new item. And then, you just make a CPP file, which is that. So once you actually create a file, your setup looks a little like this. So you'll have like just your standard CPP file. But once you downloaded those dependencies that I linked to you earlier, the issue is how do you get them set up in Visual Studio? And so the way you actually do that is so make sure you put them in like some folder that you can easily access. So for example, I've installed all my libraries in here. I can show you where I keep that. So what I've done here is I have a folder where I keep most of what I do. If I can zoom in. Yeah, so I have a folder where I keep most of my things here. But what I did is I kept all of my installed libraries under just this directory. And these are where I've placed all my dependencies. So if we go back to Visual Studio, right? If we go to project, and we have to go to the properties of a project, and there's a couple things we have to configure. So firstly, we have to tell, Visual Studio, hey, my libraries are all here. So first thing I do anyway is I go to under C and C++, I go to general, and I add the include directories, right? And so this is actually where, primarily, and I go under edit, and this is where all of our libraries are stored. If I can, I guess I'll try. So this is actually, so these are the libraries and directories I've added to actually access OpenGL. And that's important because that includes all your header files. So if you're familiar with C and C++, you have all your header files there. But you have to have some include directory, right? So that's the first thing you do. And then secondly, what you have to do is you have to go to linker and and you should include an additional library directive or directory. And the reason I include this is for GLFW, because GLFW, when you download the binaries, that includes the library itself. So that's why I have this additional library directory, because I'm using GLFW in a separate folder. And that library folder is actually used when we include the additional dependencies. So this is actually the most important part, where we actually include all of our main dependencies. So like I said, GLFW, that is what relies on that additional library directories. You don't have to worry about glue32 and OpenGL. You should add those, but glue32 and OpenGL already come with Windows anyway, and they should be there, so you don't have to worry about those. I might be kind of rushing through setup here, but let's actually get started making a window. So let me first uncomment our other example before I get started here. So let's kind of walk through how we would actually draw a window. So first things first is we have to make sure we have all of our included files. Let me see, is that, yeah, let's zoom closer. So first we have to make sure that we actually have all of our include files going forward. So you always include GLAD. Oh, and also, I guess that reminds me, this GLAD is used for extensions, like I mentioned, but when you actually make your project, when you download GLAD, it also comes with a C source file. Make sure you add that into your project by doing add and then existing item, and then you find wherever GLAD would be for you. I've already added it here, but just make sure you include glad.c under your source files. So once you've done that, you set it. So you include the necessary files for OpenGL and GLFW. Well, GLAD and GLFW. And so first thing you actually do is you initialize GLFW, and then you basically tell what version of OpenGL you're going to use. So in this case, I'm going to use version 4.5. And then what I'm going to do is just use the core profile. So this is just kind of the core of OpenGL. So sort of what goes, so it's sort of general here. And then what I do next is I basically make this. So this is our actual window, right? This is the variable that holds our window. And we do this by calling create window. We pass in the width, and then we pass in the height. And we also pass in the window title here. And then these two can just be left as 0 or just null for now. And it's always good practice to make sure that your window is not null, or that your window actually did create itself. So you can just do this by check, or just just ask, just exclamation mark window. That's fine. Just make sure you print out an error, then terminate. And so this is so then we use this function make context current. That actually, and that takes in a window parameter. So that actually makes that window parameter like a current context. So that's actually the focus of our program. So this is kind of what makes our window the focus of our program, or the focus of our current context. And then finally, or secondly, what we have to do is we have to actually tell GLAD to load up. And this is done through this function called GLAD load GL loader. So this loads GLAD and everything else you need. And basically what we're doing here is we're basically checking that GLAD has properly initialized. So if it is not properly initialized, we throw an error and we exit out of the program. Okay, so now this is kind of getting into the more important stuff, I think. So this function here, GL viewport, what this does is it actually maps 124 by 7680 to 0 to 1. So the way OpenGL works is that your window is actually a coordinate space from 0 to 1. So you guys know how you have Cartesian coordinate spaces, right? So like, your typical graph where you have like x, and y, and that might range from whatever values. So in this case here, what we do is we actually map x's 0 to 1 to 1024, and then y's 0 to 1 to 7680. And I think to visualize this, I brought up kind of a graph here. So like imagine this corner goes from 0, 0, 10, from 0, 0. Well, it says 0, 0, but let's say you go to this bottom corner where this is 1, 1, right? This now becomes 124, 7680. So we kind of basically transform that 1, 1 coordinate, or that 1, 1 point to 1024 by 7680. Does that make sense? Okay. So basically that's what GL viewport does. And this is our main event loop, right? So what this does is it basically just keeps running this program until we've closed the window. And so first thing we have to do is, well, actually, I'll talk about these two in a bit. But first thing we have to do is we have to pull for events. And what does that mean? So in GLFW, you can actually take in key presses and make the key presses do certain actions. Like, for example, you can make a resizable window that falls under event, or maybe you can move your camera with your mouse that falls under an event. And this basically just constantly is looking for an event going on. And we can actually call this through event handlers, but this is kind of out of scope for this workshop. Though the resources I've linked will probably give you more detail about that. And then what we do here afterwards is we swap buffers. Now, what does that actually mean? So in graphics, we have basically two buffers, or two basically kind of windows, or two like panes. Think about it like this: two panes that actually work together to display your image on the screen. So the reason you want to swap buffers is because when you're displaying an image, it's not instantaneous. So let's go back to our graphic here, right? So the way an image is typically rendered is you go from left to right like this to the edge of the screen, and then so up to down, left to right. So you basically keep going like this. And this is for every line. This is basically kind of how you would render it. But the problem with this is that it's not instantaneous. So in order to actually fix that, we have something called a front buffer and a back buffer. So whenever, so the back buffer actually deals with all the rendering data. So like, do you have a triangle? Is your triangle blue? Whatever. So the back buffer is what deals with that. And so once that's done rendering, it swaps over. So now so now that back buffer is actually in the screen, and that is actually what displays all your things. So the reason why you can't have one buffer is because you'll get artifacts like flicking because it's not instantaneous. That's why you want to swap buffers between your front and your back. So once we've done that, we basically just keep looping. And then once we're done with everything, we just terminate GLFW. So we kind of clean up after ourselves and we return 0. So let's try running this program, see what we get. So what I have got, so it's in the other screen, but what I have gotten here is I've gotten just a black window. And if we can see that our screen is 1024 by 7680, or our window is, and that we just have this title that we've declared before, OpenGL Workshop. And I guess this is a nice start, right? Pretty simple digest. But what if we want to like, make everything kind of pretty, right? Well, what we can do is if I swap back here, we can actually make a different color background. And we can use that by considering these GL clear color and the clear color buffer. Well, yeah, GL clear and GL clear color. What these do basically is clear color sets this clear color buffer bit to whatever color this is, and then GL clear basically clears the screen with that color. So now when I actually put up stuff, you'll probably see more red and blue kind of, probably like a magenta mix. So if we take a look, we have a nice kind of magenta window. But that's basically how we kind of get started rendering windows. So now I guess we'll actually start to get into the real graphics discussion. So if we go back to our slides here, basically, okay, so yeah. So let's talk about the graphics pipeline. So what is the graphics pipeline? So it is basically these steps our system or our graphics system takes to render images onto the screen. And this is done in multiple steps where you have a vertex shader, your shape assembly, your geometry shader, and so on and so forth. What I will focus on is the vertex and fragment shader. The vertex shader basically kind of declares where all of your points are on the screen, while the fragment shader actually translates, what points have what color. Basically determines, is this pixel blue? Is this pixel red? What kind of color is this pixel? So this is kind of what I was talking about with shaders, right? And in order to actually write these shaders, you can use something called GLSL, which stands for GL or Graphics Library Shading Language. And this is typically the standard for something like OpenGL or Vulkan. You will write your shaders in this kind of C-like language. And these shader programs, they basically utilize your graphics processing unit to take some sort of input and then some sort of output where you output color, shape, so on and so forth. And so our focus for today, at least in this section anyway, is our vertex shaders and our fragment shaders. So like I said, vertex shaders determine the geometry of your vertices, and your fragment shaders sort of determine the color of your outputs. So like I said, is your pixel blue, red, so on and so forth. So let's swap back to our actual code. So let's try coming this out. Let's go over our second example. So what's going on here? So, well, first, we do our typical, setup where we create a window, check if it's all good, so on and so forth. But in order to actually start creating a shader, what we can do is we basically call this function create shader, and we tell it what kind of shader. So in this case, we're considering a vertex shader. But the question is this vertex shader needs to know where the shader we've written is. And so, like I said, it's typically done through C programs. But what we can do is that we can just declare a constant string, and we can basically make that kind of our program. So walking you through what's going on here is that basically this program, it's a simple shader that says that the position of our vertices is just the position we take in with our X, our Y, and our Z. And the alpha, or so how transparent it is just 1. So it's basically just opaque, meaning it's fully visible. And this indicates that we're using version 4.5 of OpenGL. But just know that typically we declare shaders as string constants. Though there are better ways of creating shaders. You might have an entire class for shaders. You take in some shader from another file as a parameter, and you do some file handling. And that is probably a much better way of actually working with your shaders. So the question is yes, I have these vertex shaders, right? But where does it actually get its vertices? So to answer that question, we basically give it some sort of vertices, right? And this is done through like an array of floats. So what I've done here is I basically created, this is actually for a square later on. I'll talk about that. But what I've done here is I've created a series of vertices, and these basically dictate, like where the points are on our screen. And so with these vertices, what we actually do is we pass these vertices into whatever buffer we need. And in order to talk about buffers, I need to sort of give you context about what a vertex buffer object is and a vertex array object is. I'll get to that in a bit. But coming back to where we previously were, so it needs to know a vertex shader source, right? And so basically it passes in all the data for the vertices onto this variable here. And note that this type of variable is basically just an unsigned integer. I just use GLU int because that's kind of standard for a lot of OpenGL applications where you'll use this data type. But then we actually compile shaders because shaders actually need to be compiled. So I do this with the vertex shader, and I kind of follow through and do the same thing with the fragment shader. And so then once we have both of our shaders, we actually create a shader program, and we attach the vertex shader and the fragment shader onto our actual final shader program. And then we link our final shader program with OpenGL. So I've talked about kind of how all these components work, about how a little bit about shaders, right? But the question is, how do you actually pass vertices in? So this is where vertex buffer objects and vertex array objects come in. So basically what a vertex buffer object is it stores the data of your vertices onto your GPU. Now, the question is why do we want to use a vertex buffer object? Well, the main reason we want to store them in our GPU is mostly because it's a lot more efficient to do so, right? Because we're already accessing our GPU, it's a lot more convenient to have our GPU hold where all of our vertices are rather than going somewhere else to take them from. So again, the question is how do I actually use this vertex buffer object? Well, so first what you have to actually do is you have to generate buffers for your vertex buffer object, right? And I've declared it as just VBO here. So you basically have to generate the buffers first. And then once you have done so, you basically bind the vertex buffer object as a type array buffer. So basically you're kind of telling it it's an array buffer. And then afterwards, you finally basically put all the data of your vertices into your buffer, because basically this is telling it that the array buffer is so VBO is the array buffer. And then in this line, you're basically saying, okay, pass our vertices. So basically pass how many vertices we have, or the size of vertices in bytes, and then pass the vertices in, right? And this, I don't think you have to worry too much about, but just know that basically what we're doing here is we're passing all of our, this is actually where finally we're passing all of our buffer data or vertice data into our buffers. And so so I'll talk about this EBO thing in a bit, but that's for the buffer objects, right? So the question now is, what if we want to track the state of our vertex array objects? And basically what a vertex array object is it tracks the state of your vertices. So do they change in your graphics card? That's kind of the answer, or the question a vertex array object, or VAO, tries to answer. It tries to keep a track of, do your vertices change? Have they done something else? It keeps track of the state. And so kind of a similar way to our VBOs, right? We basically have to tell basically have to generate our vertex arrays. It's a little different of a call. We have to generate our vertex arrays, and then we basically have to pass it in. So we basically bind this vertex array, and this is actually kind of starts to keep track, right? And so the VAO starts to matter when, yeah. So basically now we've already binded the VAO, so now we kind of have a way to keep track of state. And so afterwards, what we have to do is we basically have to say, okay, well, what do I want to draw? And this basically sets the attributes for our actual triangle, right? So this actually says, okay, draw 3 points, and it's a float type, and it's 3 times the size of float, and so on and so forth. And then this basically just enables kind of what we're seeing here on screen. And so then this is actually where we draw our triangle elements. For now, I'm going to see if I can just comment this out and just show you that we draw. This is actually where we draw our vertex arrays, and we'll draw just 3 points, and they're considered of type GL triangles. And I think it's the same as this program. So, and then obviously we have to clean up afterwards. We have to delete our shader program, our vertex buffer objects, and so on and so forth. So let's try running this and see what happens. So voila, take a look at that. That's a triangle. So you're probably wondering, well, why is it just this triangle? Why is it just this weird triangle? Well, that's because if we go back to our code a little bit, I have declared basically the first 3 vertices of this. The first 3 vertices are 0.5, 0.50, and then they take on these coordinates in the x and the y. So if we think about it, right, like remember how I said earlier that that our thing goes from 0, 0 to 0 to 1, 1, right? So 0.5, 0.5 is basically saying, okay, this is our first point, right? So this is kind of our first point into here. And then 0.5, negative 0.5 is this point here. And then negative 0.5, negative 0.5 is, well, actually, I probably flipped that. But just know that these 3 vertices, these 3 actually draw. They're actually the points declared by our triangle, right? And now I guess another question too is, how do we get a red color? Sure, I've drawn the triangle, but how do we get a red color? Well, again, that's actually determined by our fragment shader. So what I've done, so our fragment shader is really similar to our vertex shader, where I create a program, but now I basically told it, okay, well, basically just make the color of everything just be a strong red and only slight amounts of green and blue. So another thing to keep in mind is that basically we use a red, green, blue alpha system, meaning that the first color determines how strong the red component is, just how strong the red color is. And then the second is green, third is blue, and then the last one is alpha. So talking about transparency, what I discussed. So, and the thing to keep in mind too is that these only take in values between 0 and 1. So meaning that 0.9 is a very strong red, and 0 is a very, and so if I change this to example, say 0, right? And let's try quitting our program and running again, right? If I show you this, because we kind of get a darker sort of triangle, because remember, our red component is nothing, but we still have a little green and we still have a little blue. That's why it's kind of this dark turquoise-ish color. So that's why so this fragment shader, like I said, it's important. It determines the actual color of your pixels and your vertices. So I'll just change that back to red for now. So now the question is so I mentioned this element buffer object here thing here earlier, right? So the question is why do you want to use element buffer objects? So let's say, for example, we want to draw a rectangle, right? If we were to use just triangles to draw a rectangle, that would just be 2 triangles, right? They would just be kind of crossed together, right? So if we go ahead and say, why don't we well, actually, yeah. So why don't we, for example, say, yeah. So what we can do here is, let's say that we want to draw from vertices. We just want to draw 6 different vertices using our vertex array objects, which I believe should work. Oh, I probably have to change that. Here, I probably have to fix that. So Yeah, let's go back. So kind of shuffling through our code here a little bit. So for now, what I'll do is I'm just going to change. Actually, yeah, I can just do, well, in any case, just know that, yeah. So what if we want to draw a rectangle, right? Like I said earlier. So what we can do is we can draw two separate triangles, right? And then have them there, which maybe, well, in any case, yeah. So what we could do is we could draw two separate triangles, and that would be fine, right? But the problem is that you're actually having 6 different vertices. So you have 6 different points to draw your triangle, and that's a little bit more overhead than, say, having like 1 or 2, or like having less. Like it'd be better if we had less vertices to draw a triangle. So we can do this by using an element buffer object. So this thing here, basically, what I've done is I have 4 vertices, which are actually all part of a triangle. So let's go back to our drawing board here. And let's see. Yeah. And so we can think of it as like, So we can think of it as like 1 point here, 1 point here, and then 2 more points like this. Sorry for the bad drawing, but we can think of it as like that these are the vertice positions, right? And so we can draw it as like 2 triangles. If I can get my skills right, we can draw as 2 triangles, right? So like one like this, and then another one kind of like this. Excuse my MS Paint skills. So we can basically draw our triangles like this, right? And that actually was what I was trying to do earlier, right? We can draw 2 separate triangles like that. And technically this is what we're doing as well. But rather than like saying 1 vertex here, 1 vertex here, and then have like overlapping vertices, we just have 4 vertices. And so that's why we want to use element buffer objects, so we can reuse our previous vertices that we've defined. And this is why I put such emphasis on this EBO thing. And so kind of similar to what we've done with our vertex buffer objects, we have to make sure we generate our buffers, and we have to basically pass all the data from our indices, except this time we pass our data of the indices into our EBO. And then we basically do a similar thing here. And so what we can do now is I can try to uncomment this, and I can show you. So draw 6 on, which I don't. Yeah, so take a look. So now we actually have a square. And so, like I said, we only use 4 vertices for that. We're still drawing 2 triangles, except instead of using 6 vertices, where we draw each triangle individually, we can share some of the vertices. That's why this is so powerful. And it's very critical sometimes to performance anyway. I know that was perhaps a bit of a tough example. Does anyone have any questions so far? Was that relatively easy to follow? I hope. It's a little complicated, I know. Moving onwards, I might be going a little quick here. So moving onwards, now this is probably the most difficult part, all the math talk. So math might make you want to throw up. Yeah, sometimes makes you want to throw up too. So why do we even bother with this math? Well, what if we want to move objects, right? So I showed you that kind of pretty rectangular or square. What if we actually wanted to move it, right? We probably don't want to have a static rectangle just sitting there, right? So we can use matrices to actually shift over our objects. We can basically make them either rotate, move, or scale. So what that means is basically make it bigger or smaller. So for context, matrices are rectangular arrays which contain numbers. They have basically rows and columns, and these rows and columns define the dimensions. So for like a 3x3 matrix is 3 rows, 3 columns. 2x2 matrix is 2 rows, 2 columns. A 2x3 matrix is 2 rows, 3 columns. And so I do mention this identity matrix, and that's sort of important because a lot of our ways we use to move our shapes are actually done through the identity matrix, or we initialize them as the identity matrix, or they utilize the identity matrix. That's why they're so important. And so to complement our matrices, we also have vectors. Now, for those of you who don't know, vectors are basically just numbers with length and direction. So if you remember Despicable Me, the villain said, I'm vector with magnitude and direction. So he was kind of right. So vectors just have magnitude and direction. So they have some sort of length, and then they have some, where are they pointing to? So this example here, this 251 example here, that just means 2 units into the X direction, 5 units into the Y direction, and 1 unit into the Z direction. And I also included this convention thing. So OpenGL basically has these axes where Y is going upwards, X is going to the right or left, and Z is going either towards you or away from you. So typically by convention, you can use something called the right-hand rule, where you can point your thumb to the right, and then you point your index finger up, and then your middle finger is the result of where you're actually pointing to. So that's kind of a convention you can use to determine your coordinates. So just remember that in OpenGL, it's Y is up and down, X is left to right, and Z is towards you or away from you. So the main operator we're more concerned about is matrix multiplication, because like I said, the power in matrices is being able to move or shift or rotate objects. And matrix multiplication is the most important thing to actually shift these objects. And so how that works is basically so the matrix, the only rule you have to make sure you have with multiplying matrices is that the columns of the left-hand matrix are the same as the rows of the right-hand matrix. And the result is the rows of the left-hand matrix and by the columns of the right-hand matrix. And so I've kind of highlighted it there in our example. And typically the way this is done is you go through row and column. So for example, that very first unit is basically the first row multiplied by each element of the column. And this is just that one column there. So in this case, this would be 1 multiplied by the 1 in that column, 2 multiplied by that 2 in that column, or 2 in the first row multiplied by the 2 in the column, and 3 in the first row multiplied by that 3 in the column. And a similar thing applies to the next one, except you may have noticed there's a bit of a mistake there. Basically, the second one kind of works the same thing, where you have 4 multiplied by 1, added by 5 multiplied by 2, added by 6 multiplied by 3, and that actually makes that middle column entry right there. I know I'm going kind of quick with this, but I hope it's somewhat easy to understand. So this is actually where now all of our talk starts to matter. So the first transformation is called a translation, and this basically just shifts our vectors, right? So whatever, so vectors can also be used to describe a point, but basically translation shifts our vectors by some amount. So for example, let's say I wanted to shift our X by 5 units, or by 1 unit, Y by 2 units, and our Z 5 units back. Well, we can basically multiply our current vectors of X, Y, and Z, and that one just stays the same. It's just by convention, it stays the same. We basically multiply this matrix by this vector, and our result is this basically just this vector with these modified, with basically just adding in these modified positions. And so, like I said earlier, it's matrix multiplication. So notice, so it's the first row multiplied by all the entries in that column there. So it's 1 times X, and then Y and Z are 0, and then that 1 stays as 1. And so that's why you get this. Same thing with Y and Z. And so let's actually look at an example. So here I've included a picture of what happens if you leave your vector. So our vector, like I said, just can describe position. So let's say we leave our the center of our rectangle as 0, 0, 0, right? We haven't shifted it from the origin. Or, well, more accurately, I guess actually to correct myself, I think this is more of actually no, that's fine. Yeah, never mind. But let's say it's just staying there. Our rectangle from earlier is staying there. If we apply a translation, 0.1 units in the X, 0.2 units in the Y, and minus 0.5 units in the Z, you would actually see that our rectangle does move slightly to the X and the Y up by a bit. Now, the Z doesn't really matter in this case because we're only doing 2 dimensions. Like, this is only a 2-dimensional rectangle. That's why you don't actually see any change in the Z. Or if you do, it's difficult to notice. But just know that translation is a way of moving objects like this. And so a similar principle applies to scaling, where we can make objects bigger or smaller by scaling them a certain amount. So this, again, this is an example where if we want, we apply 2, 3, and 1 to our X, Y, and Z, we would get a resulting matrix that is, X increased by magnitude of 2, Y increased by magnitude of 3, and so on and so forth. So this is an example of scaling where we have our unmodified rectangle and then our modified rectangle where we actually scale it by 1.9 times. And you'll see that this is you'll see that this rectangle now is almost covers the entire screen. I didn't cover it all the way, mostly just so you can see that it's still within this black, it's still within the window. But yeah, that's basically how it works. Now, finally, the last transformation we'll talk about is rotation. So what if you actually want to rotate a vector a certain way, right? Like, you might get some really cool effects through rotating. So what you can do is you can use a similar concept where you multiply the matrices, except you have these very specialized matrices where if you'll notice on the X, so for X, the row and the column of that very first one is not modified. But if you look at the Y, same thing applies where that second column and second row aren't modified at all. And same thing with Z. And they're basically just shifting it by some angle theta. And you apply and you basically multiply this with your matrix and you get these resulting vectors. So, like for example, I'll rotate X. X stays the same, but our Y and Z are changed so that it's cosine Y minus sine theta Z. And then for your Z, it's sine theta times Y plus cosine theta times Z. And again, this one stays the same. So here I have included an example. I tried showing this as a wireframe, and what that means is you only actually have the outlines of your shapes. But here's a couple of examples. So the leftmost one is a rotation around the y-axis. The middle one is a rotation around the x-axis, and the last one is a rotation around the z-axis. And so the rotation around the y-axis, like remember what I said earlier, only the x and the z components are being modified. So we're going back to our convention of y being up, right? If I can, yeah, y being up and x and z being the flat, kind of the flat plane, we can see that if we rotate around the y, we can see that x and z are actually only changing, and it's still our rectangle or square or cube, I guess, is still sort of upright. And then applying a similar concept to the x and the z axis, like in the x axis, you're rotating around it, but your y and your z components are being modified. So now the question is, how do we actually apply these transformations? So we'll use GLM and just for convenience, because it's very easy to make a matrix and multiply matrices together. It kind of does a lot of heavy lifting for us. But in order to actually transform your vector or your rectangle, you need to be concerned about the order of transforms. And so they go in like a backwards notation. So for example, if you wanted to translate or if you wanted to scale, then translate our vector, you would first multiply it by the translate matrix and then multiply it by the scale matrix. Although, you might be used to saying, okay, well, if I'm scaling first, shouldn't I multiply by the scale and then multiply by the translate matrix? Well, again, matrix multiplication is kind of weird where we have to actually do it in a backwards order where we translate then scale. So seeing this in action, right? If I translate first, then scale, right? Versus scale, then translate, or I guess I have this backwards. But this is the left-hand side is what I was talking about mathematically, where I scale first, then translate. Oh yeah, actually this is backwards, sorry. Yeah, where I scale first, then translate, versus where if I translate first, then scale. So you'll notice that the left-hand one looks a lot cleaner than the right-hand one, doesn't it? Well, yeah, again, that's because the order in matrix multiplication truly does matter. So to show you how this all works, let's actually look at a code example here. So what I'm going to do is I'm going to comment. I'm going to go ahead and comment all this out from our second program, and we're going to move on to our third program. So, so first things first, the only difference from our previous program is now I have basically made 36, I've made, I believe like 36 vertices. But what I've done here is, because a cube has 6 sides, and you have, 4 vertices per side. So I think you'll get like, I'm actually not too sure on the calculation, but just know that these vertices are here because, that's because we basically break this cube down into a bunch of triangles, right? So each face of the cube has 2 triangles attached. So you have 2 on the front, 2 on the back, 2 on the sides, and then 2 on the top and the bottom. So that's 12 triangles for a total 6 vertices, if that makes sense. And so what we're actually going to do is just for now we're going to ignore the element buffer object I discussed because we're not really concerned about efficiency, and we're just going to straight up draw, a bunch of triangles on the screen and get a cube. So now, I've kind of talked about how this cube works. So what if I want to actually, apply some sort of transformation to it? Well, like I said, what's convenient is we can actually so let me look at my shader program first. So our shader program hasn't actually changed, right? But the only difference there are our vertex shader, right? Because that determines where the vertices are. So the thing with the vertex shader is that you actually do have to modify it so that your points, your vectors actually transformed by your transformation matrix, right? So that's the only modification I've made so far to this vertex shader program, right? And so if we go down here, right? So I'm basically telling it to multiply our positions by our transforms. And so the question is how do we actually link, or how do we use these transforms, and then how do we link them to our program? Well, what we can do is first, what we do typically is we make our transformation matrix. So we just initialize it as an identity matrix. So remember that matrix earlier where all the diagonals are 1? That is our identity matrix. And we're going to call this one just a transform matrix, right? And so let's say that we, for now, what we want to do is we just want to scale it by 1.5 times. And then maybe we just want to apply our other transforms that I've shown you earlier, where we just scale where we scale first, then translate. So if we, so basically, this also, just to note, this function here, this uses our shader program. And so after you've linked it, you actually have to use it in code, and this is what this program does. But after that, what I do is I basically, from our shader program, I tell it to find whatever transform is, whatever that transform variable is, right? And then I basically assign it to this variable. And then once I do so, I basically say, okay, well, this trans variable that I have, that is actually assigned to whatever variable I've declared here earlier. So that's why I do these 2 lines here, so to actually map our transformation matrix to the transform in our shader program. So if we go ahead and compile, I believe I should see, yeah. So this here, like if you look, we actually, if you notice that before our rectangle was kind of centered, now if you notice that it's scaled, then translate. So you can see that actually has shifted versus if we were to maybe say, for example, let's say I kind of ignored the transforms here. Like let's say instead we just have an identity matrix, right? If we run this program, we can actually see that our magenta cube is just there. It is just at the origin. It has not been scaled, nor has it been moved. So we can also do some other cool things with this magenta cube. So I know I described rotation, right? So what if I actually want to rotate over time, just to kind of do some cool stuff? So what if I actually want to rotate over time? Well, what we can actually do is GLFW comes with a function called GLFW get time, and basically that just gets the current time. And so what I can do is basically just say, okay, well, can you rotate the transformation matrix over time? And then these are actually how much in the X, Y, and Z we rotate. So let's say we want to rotate only in, I don't know, say the Y, well, say some mixture of the X and some mixture in Z. So remember, like I said earlier, if we're just rotating on the Y, that's just upwards. But if we're just rotating on the X, that's just on its side. So if we have a mixture of X and Y, we're actually kind of rotating sort of diagonally, so kind of arc, sort of angled a little. So if we actually compile this program, oops, I can correct that. So if we compile this program, oops, my bad. I don't know if StreamYard, I think StreamYard's fine. Oops, sorry about that. Okay, Yeah, or let me correct that actually. Sorry guys, technical difficulties. Okay, that's better. Yeah, okay. So sorry. So if we, I think, is that correct? So if I go ahead and compile this program and I just rotate, which I think that's right? Oh, yeah, I compile. So take a look. Because I've actually rendered a cube, right? I've actually just told this thing to rotate over time in the X and the Y axes. And that's actually why you're seeing that cube kind of rotate sort of angled. And again, we've drawn 36 vertices. And although it's kind of hard to actually see the depth, right? They actually are kind of layered on top of each other. So to actually give you, I guess, a bit more of a better visual, right? So what if, for example, I don't actually have any depth, right? So this actually goes into something called Z buffering. And so Z buffering is actually important because, let me show you. Well, actually, you can't really tell here because there's no texture. But another thing to note is that if you actually apply texture to this, you may see that the actual triangles rendered are going to be a lot uglier, and they may overlap each other. And that's because there's no testing of depth, where the further triangle appears closer and the near triangle appears further, even though they really shouldn't be, but the program thinks it does. So that's actually why we have this GL-enabled depth test, because this actually enables the Z buffering. And it actually makes and if we were to apply textures and we can actually see a difference between the triangles, this actually kind of, it actually makes it a lot cleaner. And I can also enable wireframe. And so what wireframe means is kind of what I showed you earlier. It's just outlining the actual lines between your triangles. So if we look at our cube, we can actually see that there's 2 triangles per face. There's actually just 2 triangles per face. So to conclude this workshop, what I'm going to do is I'm actually going to show you how do we actually maybe we want to, I don't know, mess around with the camera, right? Or actually, let's say we want to actually make our colors change over time. Well, we can actually do that through sine and cosine, or basically our sine and cosine functions, because they only go between 0 and 1. We can actually kind of use them to mess around with the color of our vertices. And so we can do that by, we can modify this fragment shader source, and we can add in this variable called time. And so we can basically make the color change over time. And so what we do, and so let's say we want to shift red across time, we can use sine, and then we can take the sine of time to basically shift the red over some period of time. And maybe we also want to shift, by the y by cosine, and maybe we want to multiply it by 0.2, so, or maybe 0.5. So this will basically just change the color over time. And then what we can do is, once we've told it, okay, well, we want to shift over time in our shader program, over here in our actual shader, we can do is we can actually basically say, okay, find this variable or find this float inside of our shader program called time, and then basically assign this time to be our current time. So if we actually compile that now, well, actually, I still have wireframe on, but you can actually, here, I can show you. So I still have wireframe on, but you can actually see that the colors are changing over time. And so, in fact, let me turn off, the wireframe just to show you guys what's going on. I know I'm a little over time, but I will try to make this quick, but let's see, just to show you what's going on. So finally, actually show you, we've done that. We now have a cube that kind of shifts over the red and the green over time, and it sort of goes back from 0 to 1. We can actually apply the same time concept to our vertex shader here, and we can actually say, okay, over time, maybe we want to change the X and the Y. For now, I won't go into that because we're a little over time. I just want to wrap up this workshop really quickly. So to wrap up, so I talked about transformers. I talked about really kind of basic drawing shapes. The question is, where do you go from here, right? The disconnect's a bit huge, isn't it? Like I've only taught you how to draw a triangle. I've only taught you how to draw a cube and how to color a cube. But the question is how do actual developers develop, well, video games and actual applications in OpenGL? So the answer to this is a lot of setup, and it's a lot of time. But to kind of give you a bit, I guess, a bit more of a practical perspective, more modern games have started to move to Vulkan, and the reason we shift to Vulkan is because of performance. While there is a lot more to set up, the thing with Vulkan is that, yeah, it does take more boilerplate code, so you have to do more stuff. Like you have to map a logical device to your actual GPU. So there's more setup in code, but you do get more performance since you get to enable or disable certain things. And so the question is how do video games have custom models? Well, what you can do is you can use libraries like ACM or simple OBJ loader, and you can load these models into OpenGL and render them. And same thing with soil. You can actually load external textures and put them in here. And I've also linked some other fantastic resources. I would recommend at least reading through these. They're pretty comprehensive. With that being said, I apologize for going over time, but thank you for coming today. Oh, by the way, sign if you have not gotten it.